Hello everyone, and thanks for being here listening to our talk. My talk today is about computationally efficient truthful mechanisms for larger scale peer-to-peer ride-sharing systems. So we've heard a number of very excellent talks that focus more on autonomy and connectivity, and this talk is going to be focusing on shared mobility systems. And contrary to the previous talks, this one is a little more theoretical. So I think it is great for my self-esteem that not everyone is sharing their screen. Let me get started. Let me start by providing some context on the problem we are trying to solve. Shared mobility systems in general are systems that compromise, or shared mobility comprises transportation services that are shared among users. And one type of shared mobility system is a peer-to-peer ride-sharing system. In a peer-to-peer ride-sharing system, riders and drivers who are receiving transportation services and using their vehicles to serve riders respectively, these people are all traveling in order to engage their own activities and then not for the mere purpose of transporting passengers. And this is what differentiates a peer-to-peer ride-sharing system from companies like Uber and Lyft, in which drivers are only traveling in order to transport passengers. So in this talk, we'll be focusing on peer-to-peer ride-sharing systems and specifically dynamic ride-sharing systems in which a request for a ride can arrive at any point in time, either right when the passenger wants to start their trip or even a few hours in advance. We want to run a system that is dynamic, and so this is how the system basically is run. We have passengers and drivers who are going to announce their trips either in advance or right before they want to leave for their trips. And when they make these announcements, they're going to provide information on the origin and destinations of their trips, as well as travel time windows during which they would like to start and end their trips, and a deadline and notification deadline by which they need to be informed whether they can be served in the system or not. And so in order to take care of the dynamics of the problem, we are going to re-optimize this problem at a specific re-optimization time. So at a specific points in time, we are going to solve an optimization problem that is going to include everyone who has registered in the system, and their notification deadline lies during the next re-optimization period. And by solving this problem, we can announce who is going to pick up with whom, the route they are going to follow, and pricing and all the other details. So when it comes to system design, we could have different system design with different inputs and different pricing mechanisms that give rise to different types of systems. As for system design, we are going to use inputs that we obtain from passengers and from drivers, and as well as some private information. So these inputs include trip characteristics, again, the origin and destinations of the trips and travel time windows. And we will also ask for private information, and we will be using this private information for the purpose of pricing. Now, this private information is information that is also called passenger type. So, for example, we could be asking for people's valuation of time, and we could give them prices according to this valuation of time. So this private information is going to be used for the pricing purposes. And so we use these inputs, and the output of the system is going to be a set of allocations and a set of prices. These allocations are the routing, scheduling, and matching solutions, which are basically mapping the space of private information into the space of allocations, again, routing, scheduling, matching, and a set of prices that are using people's private information here in order to announce individualized or personalized prices for people. Now, when we want to solve these problems, there are a number of challenges. The first one is that these optimization problems are generally NP-hard, except for very specific cases of them. They're in generally NP-hard and hard to solve. And even more important than that is devising mechanisms that have specific properties when it comes to pricing. And those properties are individual rationality, social efficiency, and truthfulness. And I'm going to elaborate on them in the next slide. So basically, when we want to propose these allocations and prices to passengers and drivers, we will be looking at their utility. So an individual's utility is going to be the difference between the valuation of the service they are going to receive and the price they will be charged. Now, for riders, this valuation is going to be positive because they're going to be receiving a ride, but the price is also going to be positive. They're going to be charged a price, and the difference between them is the utility of the agent. And for drivers, this valuation is going to be negative because they are going to be incurring detour and sharing their vehicle with another passenger, but the price is going to be negative, implying that they'll be receiving fares. Now, as for specific properties that we want our system to have, one of them is individual rationality. Basically, individual rationality says that we could look at people's trip characteristics, their origin, destinations, and travel time windows, and we could match them, propose solutions only based on their travel characteristics. But there is no guarantee that people would be happy with those solutions and actually move forward to to complete their trips. In order to make sure that happens, we have to have individual rationality, which means that the utility that agents receive as a result of participating in the system should be higher than a specific value, for example, 0. So if as a result of participating in the system, you'll have negative utility, you're not going to participate in that system. Another property of a system that is well designed is truthfulness. As I mentioned, we're going to be asking people to share their private information with us. So, for example, I could ask you, what is your valuation of time if you're transporting a passenger? If your role is a driver and if you're transporting a passenger, I would compensate you based on your valuation of time. And as a driver, you would benefit maybe by not being truthful, by overstating your valuation of time in order to collect more fare. Now, a system that is well designed has a property called truthfulness, or dominant strategy incentive compatibility, which means that there is going to be a dominant strategy, that under that dominant strategy, your utility as a participant in the system is going to be maximized if you're truthful in reporting your private information. So if you are not truthful in reporting your private information, if you're reporting higher and lower, you would not benefit. So as a result of that, you would have all the incentive in the world to be truthful in sharing your private information. So it is hard devising mechanisms that have and satisfy all these properties, but there is a theorem by Clark, Grove, and Vickery. There is a mechanism called the VCG mechanism that proposes a very neat way of coming up with prices and allocations that satisfy these requirements. So the VCG mechanism solves an optimization problem, the objective function of which is to maximize the social welfare. And the prices are determined very easily by once solving a problem that includes all the agents and calculating the social welfare of that, minus, and then solving another problem that includes all the agents but one agent I. So the difference between these two social welfares can give us the valuation of the contribution of that agent in the system, and that is how we determine how much, what is the contribution of that agent and how much price they should be charged. Now, one caveat in doing this is that this allocation problem has to be solved to optimality. So this X star is basically pointing out to the optimal solution of the allocation problem. There's a theorem called the Meyerson theorem that says that even if you cannot solve this allocation problem to optimality, as long as you have an allocation rule that is monotone, you can have a mechanism that is implementable. And by monotonicity means that if I have more stuff, I can increase my social welfare. So as long as I have an algorithm that can give me better solutions, higher social welfare, as long as I'm introducing more input, then I should be good to go and I can use the VCG mechanism. And this is actually a very, one of the most important theorems in the field, and it is very useful. There are instances of the ride matching problem, the problem of matching riders and drivers in the peer-to-peer ride-sharing system that can actually be solved using a graph theory. For example, if I'm solving a one-to-one matching problem in which I have a set of riders, I have a set of drivers, and each rider can only be matched with a single driver, is called the one-to-one matching problem. Or I have a problem in which I'm still matching each rider with a single driver, but I'm offering guaranteed rides back home. This specific problem can be formulated on a graph as a mean cost flow problem. So these problems are all linear programming problems, and we do have access to efficient algorithms that can give us optimal solutions for this problem. And as a result of this, we can use the VCG mechanism. What happens is that when we want to solve more complicated instances of the ride-sharing problem, ride matching problem, for example, problems in which each driver can maybe carry multiple passengers, have multiple passengers on board at each point in time, then I do not have polynomial time efficient algorithms to solve these problems. And generally what people do is that they use heuristics, and there are a number of heuristics that are actually perform pretty well. But the problem with it is that in the context of pricing and mechanism design, if we are using heuristics, we lose that monotone property, and we cannot guarantee truthfulness that comes from the VCG mechanism. So the answer to that is using randomized mechanisms. Basically, we'll be using linear programming-based techniques, which would allow us to combine efficient computations with, while at the same time maintaining incentive compatibility. So here is how a randomized mechanism works. Instead of solving the integer problem that arises in a peer-to-peer ride matching problem, we will solve linear relaxations of those problems and find fractional allocations. Then we decompose these fractional allocations into integral allocations. And finally, we draw and charge randomized prices. And I'm going to go through all of these steps in the next few slides. So this randomized VCG mechanism is incentive compatible and individually rational, is incentive compatible in expectation, and it is individually rational, as I'll demonstrate in the next few slides. So in the next few steps, first we are going to look at the approximate algorithms that we are going to be using for the general pickup and delivery problem, that is a generalization of the ride matching problem. Then we are going to look to see how we can find fractional allocations, how we can use these fractional allocations to find integer allocations that can actually be implemented. And finally, we are going to apply this method in a case study of New York City. So this is the formulation for the general pickup and delivery problem. I don't want to get into this formulation. It's a messy formulation. It's an mixed linear integer program, and it is NP hard. We have a number of decision variables. Basically, what this problem says is that you have a number of passengers who are traveling from origins to destinations. You have a number of vehicles who are transporting these passengers, and all these vehicles and passengers have time windows that need to be satisfied. So this set of constraints ensure that all the agents, drivers, and riders are making these trips. Also, we want to make sure that riders are always accompanied by drivers and that the vehicle capacities are not exceeded. So as you can see, this is a very large problem, and it does not have a tight linear programming LP or linear programming approximation. So we use a reformulation of this problem in form of a case set packing problem. A case set packing problem is very concise generally. So the decision variable here is a binary decision variable, can take the value of 0 or 1. Basically, each XC here is a route or is a sequence of stops through which a vehicle can pick up and drop off passengers. And we only have one set of constraints that ensures that among all the possible configurations of pickup and drop-offs that can constitute a route, we want to make sure that a rider and a driver is only present in only one of these configurations or routes. So the problem itself is very concise. And so, as you can see, we have a polynomial number of constraints for each rider and driver. We just want to make sure that they appear only in one route. We want to make sure that they are not in two places at the same time. However, there is a catch because it's still an NP-hard problem. And the catch is that we have exponential number of decision variables or coalitions or columns, as you see here. However, the good thing about this k-set packing problem is that this linear relaxation has optimality gap that is very tight and as a function of the capacity of the vehicles. And another good property this formulation has is that it is easy to show that the objective function here is an affine maximizer, which means that if I solve this optimization problem, its objective function value is actually equivalent to maximizing the social welfare in the system, and this is a requirement to make sure that the VCG mechanism actually works and delivers solutions that are individually rational, that are incentive compatible. Okay, so as I mentioned, the problem with this formulation is that we have an exponential number of coalitions. So in order to solve that problem, we implement a column generation decomposition method in which instead of enumerating all the possible routes with all the possible pickups and drop-offs, we are going to start with a small subset of routes, and we are going to solve a restricted master problem according to this solution. And then after that, we are going to solve a sub-problem where we are going to find new columns to add to this, basically to add to the master problem. And this is an iterative procedure. One good thing about the sub-problems is that once we solve the master problem, and the sub-problem decomposes into the number of problems, where D is the number of drivers or vehicles in our formulation. And it basically is a shortest path problem with resource constraint that can be efficiently solved using dynamic programming. So we solve this problem, we have a solution to the linear programming relaxation of the pickup and delivery problem. The next step is taking this fractional solution and trying to find a number of integer solutions based on these fractional solutions, basically decomposing this fractional solution to integer solutions. And in order to do that, we can solve another optimization problem. Generally, there is Lovie and Swamy have proposed a method to solve this problem using the ellipsoid method. This method is numerically intractable for large problems and is slow in practice. And so we use another application of column generation based on the k-set packing problem to solve this problem. As I will show you in the case study, this is going to give us solutions faster and with a smaller integrality gaps. So here is how the solution methodology works. So first, we are going to solve an optimal, try to find an optimal fractional solution by solving the linear programming relaxation of the pickup and delivery problem. If we call that X star, then we use the VCG mechanism to obtain the fractional prices, and let's denote that by P superscript frac. This is a price for agent I. And then once we find this, we are going to decompose the fractional allocation to integral allocations using the solutions that by solving the decomposition problem we saw in the previous slide. Next, we are going to draw an allocation, an integral allocation, according to the solution of the decomposition problem with probability lambda. These lambdas come from solving this decomposition problem. And then we are going to charge randomized prices that are a function of the evaluations of the integral solutions, the fractional solution, and the fractional prices. So it is easy to show, straightforward to show that certain properties exist for this randomized mechanism. Individual rationality exists. If we have individual rationality for the original problem, as you see here, basically individual rationality for the fractional problem says that the price should be less than the valuation, meaning that the utility, which is the difference between them, has to be positive. If that holds, which it does because we are using the VCG mechanism to obtain it, then the individual rationality of the integral solutions also exists. The expected social welfare is going to be the social welfare of the original system and divided by a specific value alpha, and this alpha is the integrality gap of the allocation rule. We can show that this mechanism is truthful in expectation. So as an agent who's participating in the system, you might sometimes benefit if you are not truthful in reporting your private information, but in expectation, you would be better off if you are always truthful. And so let me just skip the proof. It's a very simple proof, but let's just skip it. So let's get to the case study of New York City. We did a case study of New York City. We have managed to solve this problem for up to 3,000 agents over the period of an hour for 3,000 agents traveling over the period of an hour in the New York City area. And what I'm showing you here is summary of results. Basically, this figure is showing us the average non-solo ridership ratio. As we are solving the decomposition problem, as we find more and more of these solutions, we can our ridership ratio, non-solo ridership ratio actually increases, but at the same time, the computational time increases. This figure is showing the computational time of finding these integral solutions from the fractional solutions as we continue with our column generation approach. So it basically tells us two things. First, that if I have more capacity on my vehicles, I'm going to be better off. And if I have, I choose a tighter stopping criteria in terms of integrality gap, I also would be better off, but it comes at a price, and that price is more computational time. The good thing about this method is that once you start the procedure, you're always going to have integral solutions that you can actually implement. If you have enough time to continue finding better solutions, you could implement them. But if not, you have more real-time requests that need response in real time, then maybe you can settle for solutions that you find initially. And over here, we have the social welfare. When social welfare is very small, this is the histogram of social welfare. When the social welfare is very small, it indicates that around zero, it indicates that a lot of people are basically traveling alone. They're not participating in the system, so their social welfare is zero. When we are on this side of the graph, right-hand side of the graph, basically we are seeing more higher social welfare values. And as you can see, higher social welfare values can be obtained when we have vehicles with higher capacities. This case shows the capacity and smaller integrality gaps. In general, we've seen anywhere between 33% to 85% improvement in social welfare by comparing this algorithm using the state-of-the-art in the literature that uses the Levy-Swarmy algorithm. That concludes my presentation, and I would be happy to answer any questions you might have.